When you strip away the interface and the marketing, generative AI has no intuition, no thoughts, and no real intelligence. It operates as a strictly sequential mathematical pipeline. Beneath the illusion of an omniscient digital brain, every single output is dictated by a rigid, precise matrix of geometric and mathematical calculations. To understand how these systems work, we have to track the exact journey of raw data passing through this pipeline until it emerges as a coherent output. This diagram outlines that complete journey. Stage 1 is data collection and tokenization, where massive sets of raw input are broken down into digestible pieces. Stage 2 is the core architecture. This is the structural engine that processes those pieces. Stage 3 introduces the training phase, where deep learning mathematics optimize the system through relentless trial and error. Stage 4 is fine-tuning and alignment. Here, the model learns behavioral compliance so it can properly interact with users. Finally, Stage 5 is inference. This is the operational phase where the fully built model generates novel outputs. This 5-step sequence provides the technical framework required to move beyond prompt engineering and into the actual mechanics of model development. The entire process begins with a strict computational limitation. Neural networks cannot process text or images directly. They can only calculate numerical matrices, known as tensors. Before a model can evaluate a single sentence, it must translate the text. This translation step is called tokenization, which breaks raw paragraphs down into foundational numerical units. But assigning a random number to a word does not capture what the word means. To solve this, the pipeline uses a mathematical encoding step called embeddings. An embedding shatters a single token into a multidimensional vector, a massive string of decimals storing its context. By plotting these onto a spatial coordinate plane, the computer groups similar concepts based on geometric proximity. Words with similar meanings land physically close together. Computer vision models follow a parallel breakdown. Instead of sentences, visual images undergo a structural deconstruction into discrete, localized pixel grids that the network can quantify. Without this critical conversion stage, the AI has no material to calculate. All human language and visual meaning is reduced strictly to spatial geometry. Once the data is tokenized, it enters the core architecture. Because text and image data behave differently, they require entirely divergent structural engines. For text generation, the undisputed engine is the transformer architecture. The power of the transformer lies in a specific internal component called the self-attention mechanism, which allows the model to map context across thousands of words. When you read a sentence, you read left to right. Self-attention analyzes every token simultaneously. It calculates attention weights to determine how one word modifies the others. High attention weights mathematically link distant tokens together, like a pronoun to its subject. What looks like advanced reading comprehension is simply the calculation of weighted vector dependencies across a massive spatial map. Image generation relies on a different architecture. The spatial counterpart to the sequential transformer is the diffusion model. Diffusion models learn through a forward process. An initially clear image is systematically corrupted by injecting random noise until the data is completely unrecognizable. To reverse this corruption, these models rely on a specialized neural network called a U-net. The U-net operates backward. It analyzes the field of static, iteratively predicts the noise pattern, and mathematically subtracts that noise from the grid. By continually predicting and stripping away noise from pure static, a completely novel visual structure inevitably emerges. Text models generate by predicting logical sequences. Vision models generate by sculpting distinct forms out of mathematical static. Designing the architecture is just the blueprint. Stage 3 is the training phase, the most computationally heavy stage of the pipeline, where deep learning calculus physically optimizes the network. Training starts with a forward pass. The system pushes input data through its network layers and attempts to predict the correct next token or pixel state. At first, the prediction is usually wrong. To quantify this error, the network uses a loss function, a rigid mathematical measurement of exactly how far off the prediction was from the actual target data. Different models use different calculus, cross-entropy loss for text and mean-squared error for vision. After calculating loss, a reverse flow corrective mechanism called backpropagation is triggered. Mathematical gradients compute adjustments, and optimizers systematically update the weight and bias values locked inside the network's nodes. This sequence of forward prediction, loss calculation, and backward correction repeats millions of times across terabytes of data. What we frequently describe as an AI learning is entirely mechanical. It is the steady minimization of error through relentless calculus. When the training phase ends, you are left with a base model. But a base model is merely a statistical autocomplete engine. It knows how to finish a sentence, but it has no concept of following a prompt. Stage 4 converts that engine into a tool. It starts with instruction tuning, which forces the model's outputs to map to specific command structures, like summarizing text or writing Python code. To finalize this behavior, engineers apply a mechanism called reinforcement learning from human feedback, or RLHF. RLHF relies on human evaluators reading outputs and ranking them based on safety, accuracy, and helpfulness. These rankings convert into a mathematical reward matrix superimposed over the network. The model updates, permanently thickening neural pathways that yield high human rewards and penalizing lower-ranked paths. Alignment provides an artificial behavioral layer. It takes the cold probability calculations of the base model and shapes them into what feels like an intelligent, helpful assistant. The fifth and final stage is inference. This is the stage you actually interact with the moment you type a prompt into an interface. During inference, the model does not learn. Its billions of internal weights are completely frozen. It simply applies its trained architecture to your novel, real-world input. To generate its response, the model relies on a logic loop called autoregressive generation. Despite its massive size, an autoregressive language model operates under a strict limitation. It can only predict one single token at a time. Once that single new token is predicted, it is physically appended to your original prompt. That entire updated sequence is then fed back into the start of the model to predict the second token. This loop runs autonomously, token by token, continually expanding the input until the mathematical sequence outputs a designated stop token, halting the process. From breaking down data in tokenization to applying the architecture, minimizing error during training, aligning behavior through RLHF, and finally executing the inference loop. Whether building transformer-based LLMs or denoising visual fields in diffusion models, every optimization in generative AI occurs within this 5-stage bedrock.